The GSLV Mark III, the third generation GSLV, inherits various technologies from its predecessors. It's very different in terms of its stages, structure, size, and has double the payload carrying capacity than the Mark II version. Nearly 43.5 meter tall and with a lift-off mass of 641 tons, ISRO's GSLV Mark III T2 is about to roar once again at the second launch pad at SDSC Shar.
Geosynchronous Satellite Launch Vehicle Mark III is the heaviest launch vehicle of India. GSLV Mark III is capable of lifting up to 4-ton mass to geosynchronous transfer orbit or a 10-ton payload to low Earth orbit. This vehicle is powered by two S200 solid motors, one L110 liquid core stage and a powerful liquid cryogenic stage C25. This mission is second developmental flight of GSLV Mark III, and this is important mission for GSLV Mark III program, as after the success of this mission, GSLV Mark III will be declared as operational and will join the group of operational vehicles PSLV and GSLV. The payload for GSLV Mark III D2 is a very advanced high throughput satellite GSAT-29, which is a multi-band, multi-beam communication satellite with a lift-off mass of 3.4 ton. GSAT-29 payloads are configured to cater to the communication requirements of users from Jammu and Kashmir and northeastern regions of India. Apart from these operational requirements, the satellite would be demonstrating several new and critical technologies also.
The first stage of this giant vehicle consists of two S200 boosters, which are 26.2 meters long and 3.2 meters in diameter. Each has a capacity of carrying 205 tons of solid propellant. S200 is the third largest solid rocket motor in the world. The L110 core stage carries 116 tons of earth-storable liquid propellant. It is nearly 21.4 meters long and 4 meters in diameter. It employs two enhanced thrust Vikas engines. The 13.5 meter long indigenous C25 cryogenic upper stage forms the third stage of the vehicle. It uses 28.6 tons of supercooled liquid hydrogen and liquid oxygen, which provides more thrust for every kilogram of propellant burned compared to conventional liquid propellants. On top of the third stage is the spacecraft in the 5-meter diameter payload fairing. The first successful experimental flight of GSLV Mark III took place in 2014 when it carried a crew module as its payload. Both its solid and liquid propulsion stages had performed well, and the vehicle was proven in the atmospheric flight regime. The first developmental flight of GSLV Mark III successfully launched India's high-throughput communication satellite, GSAT-19, weighing 3,136 kilograms on 5th June 2017. In this GSLV Mark III D2 mission, the rocket will carry the 3,423 kilogram GSAT-29 communication satellite into geosynchronous transfer orbit. GSAT-29 is a forerunner of future advanced communication satellites of INSAT and GSAT series. Its Ku and Ka band communication payloads are designed to mainly focus on providing high-throughput connectivity to the large population of the country, including the ones in hilly and geographically inaccessible areas of Northeast and Jammu and Kashmir regions. The satellite is also a test laboratory for several new technologies. It is a 3-axis stabilized geostationary satellite configured on ISRO's enhanced I3K bus. The satellite has a multi-band, multi-beam payload, which is essentially meant for demonstrating new technologies. The Ku-band payload of the spacecraft comprises transponders for Northeast and for Jammu and Kashmir regions. The two overlapping spot beams, one each over Northeast and Jammu and Kashmir regions, will provide connectivity between users carrying small terminals. The Ka-band payload consists of fixed and steerable beams to serve the country, including the Northeastern and Jammu and Kashmir regions. GSLV Mark III D2 vehicle will lift off with the simultaneous ignition of its S-200 boosters. The ignition of the liquid core stage will be at 114 seconds into the flight. Both the boosters will burn out and separate from the vehicle at 140 seconds after liftoff. At 225 seconds, the payload fairing will separate. At 317 seconds, the liquid core stage will burn out and separate from the vehicle. 2 seconds later, the C-25 stage will ignite and will burn for almost 10 minutes. Subsequently, it will shut down at 965 seconds. GSAT-29 is planned to be injected into a GTO with its perigee at 190 kilometers and apogee at 35,975 kilometers. The Master Control Facility MCF at Hassan will take over the command and control of GSAT-29 soon after its separation from GSLV Mark III D2. The satellite orbit will be raised to the final circular geostationary orbit GSO by firing liquid apogee motor in stages. Once the satellite reaches its final orbit, the solar panels and telecommunication antennas will be deployed. With the success of this flight, the development phase of GSLV Mark III vehicle program will be completed and the vehicle's operational phase will begin. Thus, GSLV Mark III D2 will be a significant milestone towards achieving self-reliance in space activities. The GSLV Mark III, the third generation GSLV, inherits various technologies from its predecessors. It's very different in terms of its stages, structure, size, and has double the payload carrying capacity than the Mark II version. Nearly 43.5 meter tall and with a liftoff mass of 641 tons, ISRO's GSLV Mark III D2 is about to roar once again at the second launch pad at SDSC Shar.
Geosynchronous Satellite Launch Vehicle Mark III is the heaviest launch vehicle of India. GSLV Mark III is capable of lifting up to 4-ton mass to geosynchronous transfer orbit or a 10-ton payload to low Earth orbit. This vehicle is powered by two S-200 solid motors, one L-110 liquid core stage and a powerful liquid cryogenic stage C-25. This mission is second developmental flight of GSLV Mark III and this is important mission for GSLV Mark III program, as after this success of this mission, GSLV Mark III will be declared as operational and will join the group of operational vehicles PSLV and GSLV. The payload for GSLV Mark III D2 is a very advanced high throughput satellite GSAT-29, which is a multi-band, multi-beam communication satellite with a liftoff mass of 3.4 ton. GSAT-29 payloads are configured to cater to the communication requirements of users from Jammu and Kashmir and northeastern regions of India. Apart from these operational requirements, the satellite would be demonstrating several new and critical technologies also.
The first stage of this giant vehicle consists of two S-200 boosters, which are 26.2 meters long and 3.2 meters in diameter. Each has a capacity of carrying 205 tons of solid propellant. S-200 is the third largest solid rocket motor in the world. The L-110 core stage carries 116 tons of Earth-storable liquid propellant. It is nearly 21.
ISRO achievements. The saga of
EPB2 initially moved eastward and then exhibited westward drift. So this particular drift could be attributed to the disturbance electric field associated with the disturbance dynamo. We also observed a larger eastward drift values towards the deep equatorial region from that different geograms which we have plotted on different latitudes. We see that there exists a presence of a latitudinal gradient in the zonal drift of EPBs during this moderately disturbed night. We also observed the diminishing of the equatorial plasma bubble during this night, and maybe the possible cause due for this diminishing is the interaction of these EPBs with the enhanced intensity region, that is anomaly, which might have generated at the deep equator and which have traveled altitudinally or latitudinally. So this was the case study was presented and published in the JGR last year. Thank you.
Thank you, Dr. Onkar, for sticking to time. In fact, we have some time for taking questions. So
Yes, sure.
the presentation is open for questions. I have a question, Dr. Onkar.
Yes.
If I understood correctly, what you said was that the radar echoes indicated that the spread F or the EPB that you saw in your imager, they are not the same, right?
Yes, yes.
Yeah. So so what caused the generation of EPB at your latitude?
Actually, in the H-F data of the Tirunal Valley,
Yeah.
there was height fluctuations prior to the
Okay.
ESF. So
Okay.
maybe some seed perturbation was there.
Ah.
And if you check the geometry of this Panala and Garanki, so whatever bubbles we have seen in the Panala location, that
need not
have
be the
not
same.
reached
Yeah.
to the garden key, or either they are disappeared before reaching
Right.
to the garden key. This is
Correct,
what we see.
Correct. Yeah. And the disturbance dynamo effect, that is what you were trying to indicate, right? That it is the interplay of the disturbance dynamo effect at your
Yes.
location.
Yes. Actually, this effect may be whatever one bubble is, got attacked by this effect. Only
Yeah.
EPB1.
Yeah.
That's the second one. And the first one was free from this effect. So it didn't move westward. This is what we thought of.
Okay. Okay. So there is like the time delay between these
Time delay,
two. Yeah.
time. Yes.
Okay. Okay. Yeah. Nice study.
Yes.
So any other question? Okay, if there are no questions, then I think we'll
Hello.
okay, I'm seeing one hand raised, Sunil. Yes, you can ask your question.
Hello. So actually, I have one basic question. Like, what is the possible reason that the disturbed electric field caused the westward drift of the plasma bubble?
Dr. Onkar?
Yes, yes.
You heard the question?
Yes, yes.
Yeah.
Actually, disturbance electric field, when it plays, means already people have studied that disturbance wind can produce a westward drift in the low latitude region, and they are much higher towards the deep equatorial region. In our case, there may be a possibility of two bubbles should interact with the disturbance wind, this dynamoelectric field. But the interdepletion distance of these two bubbles are so much large that only the trailing EPB2 got affected by this effect.
Okay, thank you.
Okay, thank you, Dr. Gaurav. So now we will move on to the Dr. Suman. You are there. We can, if you're ready, then we can go ahead with your presentation. Yeah.
Am I audible?
Yes, you're audible. Yes.
Okay, okay. So, one second, sir. Please.
It seems your problem is still persisting. No.
Yeah, can you please see my screen, sir?
Yeah, we can see your screen, but we are not seeing the presentation.
Presentation is open. Presentation is open. Can you please see? Can you see my presentation, sir?
No, no, not yet.
Not yet. What is happening?
Suman, there is a open share tray. If you click that, you have to go to full
Now-
screen sharing.
Sir, here actually open. I have opened in full screen, sir. Can you please see? Has
We
it
are not
come,
able
sir?
to see. We are not able to see.
Okay.
Okay,
Maybe what to
now
save
you are,
time, maybe what we can do is
now you are seeing, sir?
your screen we are seeing. Yes, now it has come.
Okay,
Yes.
okay. Now slides are changing, sir.
Yeah. If you can put it in the full screen mode. If not, then maybe we can. If you're able to move your slides, we will go ahead.
Yes, sir. I'm moving my slides, sir. Can you please verify?
No.
No movement.
Yeah.
But I'm moving, sir, actually. Some issues
Yeah.
there maybe, sir. Then I can probably wait some for another doctor.
Yeah. I think what we can do is maybe you can try to resolve it. You get
Yes, sir,
some
yes,
more
sir.
time, or maybe you try to present it from Dr. Nirvika's
Okay, sir. Okay,
laptop.
sir. Yes, sir.
Okay.
I'm going there. Okay. I will take a
Yes.
next time, sir. Actually. Please, sir.
All right. In the meantime, then we will move ahead to the next
Okay, sir.
presentation. Is that okay?
Yes, sir. Okay, sir. Okay, sir.
Yeah.
Okay.
Okay. Dr. Subir, you are there? Dr. Subir Mandal.
Yes, he is there.
Yes.
Had the permission to use the mic.
Yes. Yes.
Now, can you hear me?
We can hear you. We can hear you.
Okay, sir.
Yes, you can load your presentation. So the next presentation would be by Dr. Subir Mandal from Physical Research Laboratory. His title is the Daytime Thermospheric Wave Dynamics and Day-to-Day Variability in the Occurrence of Equatorial Spread F.
Okay, can you see my slide in full screen mode?
Yes, we can see. Yes.
Okay. Good afternoon, everyone. Myself, Subir Mandal. I am a postdoctoral fellow at Physical Research Laboratory. I thank the organizing committee of National Space Science Symposium for providing me with this opportunity to present my research work in this meeting. Today, I'm going to talk about the day-to-day variability in the ESF occurrence in the light of vertically upward propagating gravity waves in the daytime. So, as the name suggests, the equatorial spread F or the ESF refers to the spread in the F layer echoes as observed in the ionogram, as shown here. And they are one of the manifestation of the what we call the plasma irregularities in the equatorial ionosphere. So, atmospheric gravity waves are considered to offer the role of seed perturbation for the generation of these plasma irregularities. Once generated, these irregularities go non-linearly. Sorry. So what happened, you see, on a seemingly identical conditions, these plasma irregularities appear on one night and they remain absent on the other. And as these irregularities has a severe effect on the trans-ionospheric radio wave communication, so the key interest of the community is to understand their day-to-day variability and also to find indicators that can be used to predict their occurrence much earlier in time. So to carry out our work, what we have done, we have taken the DigiSound data from Trivandrum station. And what we have done, we have taken the non-ESF day as a control day against the backdrop of surrounding ESF days. So such selection of ESF and non-ESF days gives us the opportunity to understand the variation in different parameters from one ESF day to the next immediate non-ESF days, or the vice versa. So as the earlier work suggests that the daytime electrodynamics, their strength is conducive for the generation of these plasma irregularities. So we looked into the variation in the EEG strength for all these ESF and non-ESF days. And as you can see here, that on average, as marked by this black, this thick lines, if you can see, that the average strength for all the ESF and non-ESF days is kind of similar. But what is interesting to note here is that there are ESF days, as shown by this blue color curve, when the EEG values are negative in the afternoon sector. So this suggests that even on the days when the daytime electrodynamic is relatively weak, those days also have shown ESF generation. So that means there are other parameters. They are also playing significant role for the generation of this ESF. And also in the literature, there are reports on understanding this day-to-day variability based on the pre-sunset time equatorial electrojet strength. So similarly, we have also calculated the pre-sunset time equatorial electrojet strength. And as you can see here, in our case, we do not find very significant contrast between the ESF and non-ESF days. So based on these two figures, what I would like to convey here, that for this duration of data, EEG strength, based on the EEG strength, we are not able to comment on anything on the ESF occurrence. So now going to the another important indicator that are used for the understanding the day-to-day variability in ESF is the base height of the ionosphere. Why base height of the ionosphere is important is that if the ionosphere is at higher heights, what happens at higher heights, the collision will be less, and that conditions will be very much conducive for these plasma irregularities to sustain and grow in those less collision region. So here, to understand the base height variation, what we have done, we have plotted the evening time base ionospheric height variation for all the ESF and non-ESF days. And as you can see, for ESF days, the heights are well above 300 kilometer for most of the time, except for one day. And there are few occasions when height of the ionosphere has reached 300 kilometer and beyond, but ESF has not occurred, as marked by this pink color dotted line. So this confirms that the earlier theory that this base height of the ionosphere going beyond 300 kilometer in the evening sector, in the evening hours, is a necessary condition, but may not be a sufficient one. And also, based on this kind of contrast in the H prime F values, this information can only be obtained after the local sunset time. So, and there is another important parameter that are used to understand the day-to-day variability in the ESF occurrence is the strength in the vertical drift in the post-sunset hours. What happens if the vertical drift are stronger? What will happen? They push the ionosphere to higher altitudes where the collision are less, so the plasma irregularities will be favored. So because of that, so in this context, we have calculated the peak vertical drift in the post-sunset time for all the ESF or non-ESF days, and they are plotted here. And as you can see, there is a significant contrast can be seen in their values, with higher values on ESF days and relatively lower values on non-ESF days. But again, if you were to use this contrast to predict the occurrence of this ESF, we have to wait till the time of sunset. So now there are numerous reports available in the literature which suggests or which has showed evidence of gravitative activity prior to the occurrence of ESF, and also based on the several work on the daytime, it suggests that the daytime thermosphere prepares the conditions either conducive or otherwise for these nighttime plasma irregularities to occur. So On this background, we'd like to see how the daytime wave dynamics, especially the gravity wave activity and how their vertical propagations are varying from one ESF day to immediately next non-ESF days. So for that, what we have done, we have used the DigiZone data from Trivandrum station. And what we do to get the gravity wave information, we basically monitored the height variation of constant electron densities as shown here. And you see on occasion, these electron density height variation, they show downward phase propagation as marked by these black dashed lines. And these downward phase propagations are signatures of upward propagation of gravity waves. Now, if these height variations or these phase offset are caused by upward propagating gravity waves, then there has to be some property of the wave to be imprinted in all of them. So to confirm what we do the spectral analysis, and we see that on this day a time period is present in all of them. So therefore, a presence of a common time period and this kind of downward phase propagation confirms that there is an upward propagation of gravity wave. But to get the information for that particular gravity wave, what we do, we filter these isoelectron density contours for this particular time period, and we make use of the height and time difference information to obtain the vertical propagation speed of the gravity waves. Now what we have done, we have applied this methodology for all the ESF and non-ESF days selected for this study. And what interesting to note here, that in one of our earlier work, we see that vertical propagation is found on around 40% of the time. But if you look here, in this case, for non-ESF days, we are observing around 50% of the time. But when it comes to the ESF days, we are observing this vertical propagation signature. That means we're observing downward phase propagation and presence of common period on 85% of the time. So therefore, this clearly suggests that there is an influence of upward propagating gravity waves, and they're playing some kind of role in this day-to-day variability of the ESF. And we further carried out wavelet analysis to ascertain that these waves, what we observed, they sustain till the evening time and beyond, and to be present in the ionosphere and play the role of seed perturbation. What we have found is that when we look at the time vertical propagation speeds, we found that for ESF days, as you can see here, as marked by these blue color points, they're significantly higher compared to non-ESF days on many of the occasions. And these kind of contrast for this duration of data, we have observed as early as 14 local time. Now, in one of our earlier work, we have seen that these vertical propagation speed of gravity waves, they are influenced, they show response to the solar flux variation. Now, to confirm that whatever the variation we are observing here in the vertical speeds that are higher on ESF days compared to non-ESF days are not related to solar flux variation, we have plotted these vertical phase speeds values as a function of solar flux. As you can see, there is no systematic relation can be found between the two. Therefore, whatever the variation in the vertical propagation speeds of these gravity waves we are observing for ESF and non-ESF days, they are only due to the local dynamics. So to better represent these contrasts in phase speeds, we came up with a bar plot. And where you can see in the x-axis, if we go from left to right, we're basically going to higher speed gravity waves. And you see, as we move to the right, that is when the gravity wave speeds are higher, those days are more likely to be an ESF day compared to the non-ESF day. So far what I have presented suggests that the vertical propagation speed of the gravity waves, they play a role in the day-to-day variability of ESF occurrence, and their information can be used to predict the ESF occurrence. Now, what further we want to know is how these upward propagating gravity waves are affecting the ionosphere, because we are observing them both ESF and non-ESF days. We are observing more on ESF days. Now we have to look how they are affecting the ionosphere. So what we have done, we have compared the time periods of these upward propagating gravity waves with the time periods we are observing in the bottom side of the ionosphere and the H prime variation. And we see within the limit of Bernd-Weisela period, irrespective of ESF and no ESF days, these upward propagating gravity wave time periods are matching with the time periods observed in the H prime. So that means these neutral waves, what we are observing, they affect the bottom side of the ionosphere. Now they are affecting on both ESF and non-ESF. So what's so different on ESF day compared to the non-ESF day? So for that, what we have done, we have calculated the amplitude of perturbation in the H prime F, and we have multiplied this amplitude with the vertical propagation speed of the gravity waves. And what we see now, you see the contrast here is much more clearer here. Here you see this red corresponds to non-ESF days, and the surrounding 2 points correspond to their surrounding ESF days. And you see almost on all the cases, this parameter are showing higher values on ESF days compared to the non-ESF days. And if you look at the unit of this parameter, this is almost equivalent to the unit of energy per unit mass. So basically, they're in a way kind of representing the high-speed gravity waves on the ESF days. They are perturbing the ionosphere more efficiently compared to the non-ESF days, and that's how they are playing distinctive role on ESF and no ESF days. What we like to further is that there are occasions when
you have 3 more minutes.
Yes, sir. And what we look further is that we have observation when these vertical phase speeds are the lower values, but even though they are corresponds to ESF days. So for that, we have looked into a comparative study of this vertical phase speed of the gravity waves and the equatorial electrodynamic strength in the evening time. And you can see here is that the days, except for two occasions, when the days when the vertical propagation speed of the gravity waves are less, they are associated with the higher values of post-sunset vertical drift. So they combinedly bring out the bit or more contrasting feature or more contrasting picture in the day-to-day variability of the ESF occurrence. So what I have talked about in this presentation is that upward propagating gravity waves, they are found to be more active on ESF day compared to non-ESF days, and these vertical propagation speeds are higher on ESF days. And using such information, ESFs can be predicted much earlier in time in the day. And also these gravity waves on the ESF days, their high speed values, they perturb the ionosphere more efficiently than the non-ESF days.
Thank you. Thank you, Dr. Subir. We have a question from Dr. Patra. Dr.
Yes,
Patra. Dr. Patra, you can ask your question. We are not able to hear you. Okay, we can take other questions if there are any. Dr. Patra, you're there. Okay, we are not having his audio. Probably maybe later on we can.
Dr. Tarun, actually his mic is not working properly.
Okay.
Go ahead. We can go ahead.
Okay. All right. Then maybe we'll. Okay. I'm seeing one hand raised, Dr. Sripati. I think we will. Yeah. What we will do is we will not take the question now. Okay. I'll appreciate if you can write your question, and Subir can, Subir can answer that in the chat box. We'll go ahead with the next presentation. It will save some time.
Sure.
He's not able to find
okay.
This.
Yeah.
Okay, sir. I'm stop sharing this.
All right. So now I invite Dr. Mridula N from Space Physics Laboratory. She'll be talking about the intermediate descending layers over the equatorial location of Thiruvananthapuram.
Good evening. So today I'll be presenting the work done on the occurrence features of intermediate descending layers over the equatorial location of Thiruvananthapuram. The contributing author is Dr. Tarun Kumar Pant, and his work is in article in Press in Advances in Space Research 2022. So before going into the intermediate layers, I would like to give a brief introduction to this region, which is called as a transition region. This is a region lying between the E and F layers of the ionosphere, and the region is mainly driven by solar influence as well as the waves and tides from the atmosphere below. And hence, this is a very complex region wherein the influx from top as well as from bottom gives rise to very unique processes unique to this region. And further, earlier studies have shown the presence of gravity waves in ionosphere, and the most important outcome of the gravity waves in the transition region is to give rise to layering processes. And intermediate descending layers are one of the important layering processes taking place in the base of F region, and they form at the base of F region, and with time they evolve and move towards E region, and there and then join along with the irregularities or disappear as such. So layering processes were looked into in the past, and several studies have brought out the important role of the electric field as well as winds in the generation of the intermediate layers over low latitude region. However, the most important outcome of the layer studies is that the role of neutral dynamics like gravity waves have studies have shown that they are also capable of producing these ionization layers. And further, once these layers are formed, these layers affect the overall electrodynamics of the region as such by changing the conductivity as well as the ionization densities over this region. Hence, study of this layer is very important. Earlier, as I told, several studies in the past have brought out the role of ionization convergence, and the most important theory has been the vertical wind shear. However, over the equatorial region, where we don't have a vertical movement of ionization because the magnetic field is horizontal, the only possible mechanism is the horizontal convergence, and the most important candidate is the convergence of meridional wind. Earlier studies have shown the role of gravity wave wind shears in the formation of layers at the base of F region. Hence, giving one more indication that gravity waves play an important role in generation of processes in the ionosphere. So, when we come into the dependence of local time dependence of ionization layer formation over a deep equatorial location like Trivandrum, we find that a very clear double peak in the occurrence probability is seen, wherein we have a peak in the morning hours followed by a post-noon enhancement in the layers. And the role of chemistry as well as background dynamics are attributed to this behavior, because earlier studies have shown that whenever the ionization is getting formed, the conditions conducive for the convergence of ionization occur at times when E cross B drift has not started, as well as the ionization is increasing in this altitude region. So hence, at the times when these conditions are conducive, the generation of the layers take place, indicating that there can be an occurrence of enhanced number of layers during the morning as well as post-noon hours. When we look into the seasonal pattern of intermediate layer occurrence over an equatorial location like Trivandrum, we find that there is an enhanced occurrence during solstitial period and a decrease in occurrence during the equinoctial periods. Studies by Manju et al. And Manju and Ashwati 2016, based on the gravity wave climatology over this region, have given a clear picture of the gravity wave dynamics over an equatorial location of Trivandrum. They found that the occurrence of gravity wave activity was higher during the solstices and had a pronounced minimum during the equinoxes. So our observation also points to the fact that the gravity wave activity has a clear role in deciding the occurrence of the intermediate layers. Another interesting observation from this study is that we find that the occurrence of intermediate layers is very low during a solar maximum period 2002 compared to the 2006 period. Earlier studies by Dos Santos et al. 2019 from Brazilian longitudes have shown that there is no clear correlation between the occurrence of intermediate layers and solar activity, and they had attributed the change in the occurrence of, across the years to the movement of deep equator over the Brazilian longitudes. However, due to the fact that we have a very steady change or very little change in the deep equatorial region over the periods under study, we could very clearly look into the change of the occurrence pattern with respect to solar flux variability. And our study brought out the important fact that the intermediate layer occurrence over a deep equatorial location has a very clear relation over the solar activity, with the occurrence being higher during solar minimum periods. This is very well in tune to the current understanding of the gravity wave dynamics over the equatorial location, wherein we have a higher gravity wave activity during solar minimum periods and lower during solar maximum periods. Hence, whenever the gravity wave activity is higher, conditions require the wind shears required for the convergence of the ionization will be higher, and hence the occurrence also will be higher. Hence, there is a one-to-one correlation between the occurrence pattern as well as the gravity wave activity during this period. Further, when we look into the local time and seasonal variation of the intermediate layer parameters, we find that there is a very clear solar zenith angle variability in the intermediate layer frequency, peak frequency, and the base height. So this indicates the fact that the majority or the most important contributor to the ionization part would be the molecular ions rather than the meteoric ions, because the molecular ions very well follow the solar zenith variability. And a very clear indication that the lowering of the base height during summer season is prevalent here. This has another important implication on the duration of the intermediate layers. In our analysis, we have found that the summer layers have a higher duration compared to the other period. This could be very well evident from the fact that as the layers move towards lower heights, the molecular ions are replaced by meteoric ions, and they have a higher or a longer lifetime, which indicates that once formed, their duration will also be higher, or when the wind shear conditions are taken, it is more prominently converged during at lower heights. Hence, the role of base height in the duration of the intermediate layers over an equatorial location also has been brought out in the study. So, to conclude, the solar cycle variability of intermediate layers, which is the most important observation in this study, is highlighted, and the occurrence is high during solar minimum and low during a solar maximum period. And further, they follow solstitial maximum probability of occurrence. This, as I mentioned earlier, is correlated with the gravity wave activity over this location. Hence, this present study highlights the role of ion-neutral coupling in modulating the transition region processes. Thank you.
Thank you, Dr. Mridula, for finishing it in well within time. So I think we can take a few questions now. Questions, please. Yeah, Dr. Shripati. Yes.
Yeah, I think nice work. I just wanted to know whether you have any wind information to see how the winds were during these intermediate layers.
Exactly. With observation, we have not checked, but with numerical simulation, we have found that gravity wave wind shears of the order of gravity waves of 30 to 1 hour periodicities are able to cause convergence at the base of F layer. With actual observations, we have not checked.
I see. Because
Numerical
layers
simulation
are mostly seen at low and mid latitudes, as you already mentioned. Equatorial thing, maybe I think we need to check with the winds.
Yes, sir. Yes, sir.
Yeah, otherwise it's good.
Okay, sir.
Thank you.
Okay, thank you. Thank you, Dr. Madula. If there are no further questions, probably we can move to the next presentation. I now invite Meenakshi. Meenakshi is from National Atmospheric Research Laboratory, Gadanki. So she will be talking about tidal influence on the generation of post-midnight F-region irregularities. Dr. Meenakshi.
Good evening, sir.
Yes, we can see your slide in your audible. You can put it in full slide mode, full screen mode.
Sir, is it visible?
Yes, it's visible. Yes, go ahead.
Okay, thank you, sir. Good evening, everyone. So I'm Meenakshi, SRF from NARL. So today I'm going to present on the tidal influence on the generation of post-midnight F-region irregularities. So equatorial plasma bubbles, they are plasma depletion regions in the ionosphere, and various size scales of irregularities exist within them. It is well accepted that these bubbles are mainly generated by Rayleigh-Taylor instability that occur at magnetic equator after sunset when eastward electric field increases, leading to steep density gradient. So these irregularities, which have spatial scale half radar wavelength, they will cause intense backscatter echoes, and these FA echoes are considered to be manifestations of the plasma bubble. Usually they are observed during the post-sunset time after 18 hours, but using Indian MST radar, Patra et al. 2009 have observed post-midnight F-region FA echoes during July to August in solar minimum conditions. So the characteristics of the post-sunset FA echoes and post-midnight FA echoes are different. Their onset timing is different. And post-sunset FA echoes have direct relationship with the solar activity. Their occurrence rate maximizes during the solar maximum years, and their maximum occurrence rate during equinox month. Post-midnight FA echoes have inverse relation with the solar activity. Their occurrence rate is maximum during solar minimum years, and they maximize during June solstice month. Now, the generation mechanism of post-midnight FA echoes are still under debate. So, some proposed causative mechanisms are atmospheric gravity waves. They will be launched from active convection sites in the lower atmosphere, and they can propagate upwards, and they can cause ion-neutral collisions and generate polarization electric field, which can seed the instability. And then medium-scale traveling ionospheric disturbances, which are usually observed in mid-latitudes, and they propagate southeastward in the northern hemisphere. So they can also seed the instability. And there are certain favorable conditions for the Rayleigh-Taylor instability. And the growth rate of the Rayleigh-Taylor instability which can generate plasma bubble is given by gamma, which is equal to E by B plus E over mu in 1 by N naught dN naught by dz, where eastward electric field, B is magnetic field, mu in is ion neutral collision frequency, N naught is the plasma density, and Z is the altitude. So the eastward electric field play a very important role in the growth rate of the RTI. But during nighttime, the electric field is westward, so the growth rate will be negative. But the factor E over mu in will increase during the nighttime more than the daytime. And with the altitude of the F layer increases, G over mu in factor also increases. So the altitude of F layer play a very important role in the generation of post-midnight F-region irregularities. And what can cause this uplift of the F layer? So like, it may not be the eastward electric field, it could be the weakened westward electric field along with some sufficient recombination and plasma flux can uplift the F layer. And this weak westward electric field could be due to enhanced equatorward winds, or there might be abatement of the poleward wind. And another can be semi-diurnal variation in the zonal electric field. So we have found seasonal and interannual and longitudinal variability of F-region irregularities. At the same time, role of tides in the generation of post-midnight F-region irregularities, if any. So for the purpose, we have used radar observations, equatorial atmosphere radar, Kotatabang, and ionosonde observations from Kotatabang, Jikamarca, and Ascension Island, and Sabre temperature data for tidal analysis. So from EAR data, we have used the radar observations for the percentage of occurrence of post-midnight FAI echoes. Percentage of occurrence we have calculated as number of days when post-midnight FAI echoes are observed divided by number of days when radar observations are available. So it is clear that the PO of the post-midnight FAI echoes is very low during solar maximum year, where in solar minimum years, the PO is very large, especially during May to August. And in 2019 September, a large anomalous PO is observed for the post-midnight FAI echo over which will be investigated further. So there is an anomalous increase in the post-midnight FAI echoes in September 2019 over Kottatabang. So we have compared 2 years, 2018 and 2019. Both of them are having same solar flux. So 2018 is having a low PO in September, whereas 2019 is having a large PO of 84%. Now we have checked for the interannual variability for the percentage of occurrence of post-midnight FAI echo for September 2011, 2019. And 2019 is showing a high PO, which is highest among all these years. So the HMF2 and HPF over Kottatabang is analyzed for September 2019. And HMF2 is showing an uplift around the midnight hours. In the same time, HPF is also showing an uplift around the midnight hours. And we have calculated the vertical drift from the time derivative of HPF, which is also showing positive values over Kottatabang around midnight time. Now we have checked for the longitudinal variability in the post-midnight spreader. We have used inograms, Inosonde observations over Ascension Island and Jickamarca for 2019. So in 2019, for Ascension Island, observations are only available from July to December. For Jickamarca, whole year observations are available. And over Ascension Island, the PO of post-midnight spread-off is more. Whereas over Jickamarca, except for May, June, July, all months, post-midnight spread-off is occurrence rate is more. So again, we have checked for the interannual variability of post-midnight spread-off for September for the year 2010, 11, 12, 14, 19, and 20. These are the years when observations were available. And over Ascension Island, 2019 is having a high PO for post-midnight spread-off, whereas over Jickamarca, that high PO is not observed. So the mean diurnal HMF2 variation for September over Ascension and Jickamarca is analyzed. And over Ascension Island, we can see an uplift around the midnight time, whereas in over Jickamarca, there is a downward trend. And HPF variation is also showing a high HPF values over around midnight hours over Ascension Island, whereas Jickamarca, there is it is comparatively low. And the vertical drift is also calculated from HPF, which is found to be positive over Ascension Island, whereas over Jickamarca, it is not visible. Now to check for any modes of dominant modes of variability, we have used wavelength spectrum of HMF2 over Ascension Island and Jickamarca for September 2019. And over Ascension Island, we can see dominant mode of variability is showing periodicity of semi-diurnal periodicity, that is 12 hours. Whereas over Jickamarca, it is diurnal variation is more dominant. Now we have checked for the tidal variabilities to check. So at 10 degree north and 10 degree south, the peak equator is passing over 10 degree north in Ascension Island longitude. And for Jickamarca, it is 10 degrees south. So we have found the diurnal and semi-diurnal tidal amplitude using Sabre temperature data. So in September 2019, so in diurnal amplitude at 10 degrees south is very large compared to 10 degree north. And semi-diurnal amplitude is also showing some enhancement at 10 degree north compared to 10 degrees south during September 2019. But much enhancement is not visible, maybe because Austral SSW September 2019 was a minor event. Now we have for the relative dominance of SW2 over the DW1. So over 10 degree north, we can see the ratio of SW2 to DW1 is more than 1, showing that semi-diurnal tide is relatively dominant over diurnal tide over Ascension Island, whereas over Jickamarca, it is less than 1. So that might be the reason why PO of post-midnight spread-off is more over Ascension Island compared to Jigamarca. So the post-midnight FA echoes show maximum occurrence during June solstice month of solar minimum years, and there is a relative when there is a relative dominance of semi-diurnal tide over diurnal tide, it can favor the generation of post-midnight F region irregularities. It can be by a semi-diurnal variation in the electric field that may cause updrift of the F layer during the night time, which in turn can increase the growth rate of RTI, or it can be from winds. In meridional winds, when semi-diurnal variation is there, that can also increase the growth rate of RTI. Thank you.
Thank you, Meenakshi. It was a nice presentation. Now we are open for question. The first question, Dr. Nirvika.
Yes, sir. Meenakshi.
Yes, sir.
Just one clarification. What do you consider the midnight time? Like starting from what time?
Sir, we have considered for Kottadamang like from 10 o'clock onwards.
Do you think telling, demarcation of 10 o'clock, 10 p.m. local time is good for post midnight because you have drifting equatorial plasma bubbles from the
Yes, sir.
other longitudes coming to this, and then there is a high probability of getting those drifting patterns which may not be termed as like generated post midnight. Post midnight should be generally local time 12 o'clock and onwards. So what do you think if this definition is changed, then how much your results will change?
Sir, over Kottadamang, if you consider only from 10 o'clock, then we will have a high PO. But some days it is generated after 11 o'clock, 12 o'clock is also there. But definitely if we start considering from 12 o'clock proper midnight, definitely the PO percentage of occurrence will come down.
That's what. Then whatever come down, but it will be the true percentage, what we call the post midnight, and then your growth rate you can associate with that. But when you are telling 10 p.m. onwards, then I think a lot of issues are there. Why for the definition of post midnight itself, you are trying to change. So that I want your reply to this.
Sir, actually, when you consider from 10 o'clock, so previous studies also have considered over Kottadamang EAR data. So they have taken from 10 o'clock. So that will result in high PO during the June, when you consider the time and formation of FA echoes during that time, maximum occurrence is after 10 o'clock, means during the June solstice month over Kottadamang.
Okay, Meenakshi. Yeah. Thank you, sir.
Onakshi, there is one more question from Ramesh. His question basically is that why there are differences in the diurnal amplitudes in the northern and southern hemispheres over these tropical latitudes?
Sir, that I am not sure.
Okay. I also have a question. I was also curious in the lines of what Dr. Ramesh was asking, is that, I mean, the changes in the semi-diurnal amplitudes and the diurnal changes,
Yes, sir.
are these like more seasonal variation, or you would see it like any time?
Sir, actually, it takes like 60 days. Sabre takes to complete one full local time.
Yeah.
So you cannot get much. Small resolution is a little difficult. You need much like Sabre will take 60 days. So 1 point means 60 days. It will take to complete full local time. So that problem is there.
Right. I would like to draw your attention to some of the studies. One study was done over Indian longitudes by Dr. Divendu from PRL. That's
Okay,
about the late high tries. That was,
Okay,
I think, he was talking about the phase which was in the May-June period.
Okay, sir.
So if you can look at it, and then
Okay, sir.
yeah, so what I'm trying to understand is whether it's this, like this is a regular process which I would be seeing, or this is because of the changes in the solar activity, or you know.
Okay.
Yeah, I mean, what is the reason for this change like this, right? So yeah.
Okay, sir.
All right. Okay. So thank you. It was a very interesting presentation. So now we'll move on to the next presentation of today.
sir.
We will come back to Dr. Suman, if you're ready.
Yes, sir. Am I audible?
Yes, you're audible, and you can load your presentation.
Okay.
Meenakshi, you can unshare your presentation. Yeah. Yes.
Sir, whether my screen is visible?
Yes,
Hello?
your presentation. Yes.
Visible? Yes, sir.
Can you put it in full screen mode now?
Yes, sir. Now screens are moving.
Yes.
Slides are
Yeah.
moving, sir. Slides are moving.
No, we don't see slides moving.
Hello.
Yeah.
Hello. Yes.
Yes. Could you share your entire screen?
Yeah, that's
Suman,
exactly what
sir?
we were.
Yeah. Now is it visible?
Presentation is yet to come. Yes. Yes. Now it's fine. Yeah. Please go ahead.
Slides are changing now.
Yes. Yes. It's changing.
Okay. Then fine. Now he'll start. Okay. Okay. Okay, I'm Suman Kumar Das from National Atmospheric Research Laboratory, Gadanki. The topic of my today's presentation is assessment on the day-to-day variability of the equatorial plasma bubble. Now, what are these equatorial plasma bubbles? These are low or depleted structures in the plasma density observed in the topside ionosphere near the geometric equator. Now, this structure can produce a rapid amplitude of phase fluctuations of the radio signals, and also it can produce serious ionospheric scintillation, which can disrupt the satellite-based communication and navigation application. Now, forecasting of these structures are very much important to mitigate such issues and make the communication and navigation continuous. Now, these APVs are mostly believed to be generated by the daylight instability process, which acts at the bottom side of the ionosphere during the post-sunset hours. When the bottom side electron density is mostly being eaten up by the recombination process, and the density at the upper region remains still high. Under this condition, the density gradient acts upward and gravity acts downward, and magnetic field acts out of this plane. Under this configuration, one gravity-driven current is generated along the zonal direction, which is proportional to the density of the medium. Now, if any kind of small perturbation is present along the interface, that will create divergence in the current, and to make the current divergence free, there will be generation of polarization electric field that will further act up with the magnetic field and will take the depleted regions upward and the dense region downward with time. Now, after some time, the depleted structure will cross the topside ionosphere and it will emerge as a equatorial plasma bubble. Now, this is the growth rate of RT instability, which is taken from Sultan 1996, where the ionospheric parameters are field line integrated, where the sigma terms represent the conductivity in the E and F region respectively, where the BP represent the electric field term and U represent the vertical interval term. This is the gravity term, and this is actually bottom side density gradient, and this is recombination term. Now, along with these ionospheric parameters, there is a still need of seed structure at the bottom side of the ionosphere to overcome if it has to grow from the background noiseless fluctuation. Now, here comes the day-to-day variability of the equatorial plasma bubble. Now, the PRVS is enhanced in the zonal electric field that actually takes the bottom side ionosphere at the higher altitude, where the ionated cohesion frequency is very less. Thereby, it contributes to the growth rate to a significant amount, and it increases the possibility of EPB occurrence on a given day. Now, this PRE actually having a good relationship with the EPB occurrence on a climatological sense, but it do not show any kind of clear relationship on a day-to-day basis. Now, the zonal extent of PRE is around 30 degree, which is around 3,600 kilometers at the F region. Now, for this large longitude sector, there will be the heightened electric field not very much to influence the growth of RT instability. So the PRE cannot be the alone factor to decide the whether where EPB will grow and where EPB will not grow. So there comes the upwelling hypothesis, which shows the bottom side altitude modulation of the F layer. This is one example shown that is taken from Altair observation. This particular example has been obtained using the income scatter radar, and it shows the bottom side upliftment of the ionospheric layer by additional upliftment of 50 km, which actually helps you to attain more growth rate through the gravity term in the RT instability. So actually this uplifted portion actually later will help to EPB to occur at this particular location. Now this uprolling it can occur in a chain format. Then it is known as a large scale wave structure. Now this is a model diagram how this LSW structure actually deciding the growth of PPB at a particular longitude zone actually. So this is the observation taken from Sonoda 2015. Now with this understanding, we move forward to see to understand the day-to-day variability of the equatorial plasma bubble. For this analysis, we have used the ground-based data from Gadanki. This is a low-latitude station, and for this analysis, we consider the GD observation, that is 30 MHz 400 scatter radar, which is having scanning capability, which is used to study the onset, growth, and movement of EPBs, and also collocated DPS-4D has been also used to study the background ionospheric and seeding condition of the EPB. Now, this observed results have been further verified with the space-based observation, that is from CNOPS observation. This has been used to locate the density depletion and also to study the electric field over large longitude sector. Now we have used the data for January to April under the moderate solar active years of 2015 and 16, and all days are characterized with magnetically quiet depth. Now this is one example showing the background ionospheric condition and the manifestation in the form of EPB or at late and night. Now this observation is often using DPS for the observation, and this observation corresponds to 7th October 2015, where the bottom side height perturbation are shown here, are scaled at 567 MHz are shown here, and it can be seen the bottom side have the ionosphere has been uplifted up to 400 km on this particular day, and the vertical depth of the ionosphere has been also seen to be mean vertical depth of the ionosphere can be seen to be achieved around 45 meters per second. Now the bottom, the down to panel shows the density height perturbation, and this density perturbation has been considered at 330, 360, and 390 kilometers, and these height perturbation are taken at this 567 megahertz. Now this kind of wave structure has been taken as a proxy to understand any kind of seeding structure present in the ionosphere, as we don't have any kind of measurement of gravity waves in the neutral, because it is very difficult to get the neutral parameter, gravity parameter in the neutral. So this both the density and height perturbation show downward phase propagation, which means that there is a proper propagating gravity wave present on this particular day. Now this is from the GD observation. We can see there are two distinct EPB plumes can be seen on the particular night, and we can see from the zonal scan map made at 450 km. We can see the first EPB has this is actually this is zero. This is zonal the distance from Gadanki, and zero location represents the Gadanki location, and this is west to east distance from Gadanki. So the first EPB can be seen to be generated over to Gadanki, and has later on is drifted eastward. And the second EPB is found to be generated westward of Gadanki, and later and it has been seen overhead to Gadanki at much later time. Now at any moment this zonal structure separated by separated, and which allow to estimate their interval separation, which is in this case is found to be around 450 kilometers. Now with this Ramnath phase proportion, we estimate the wave parameters for this particular day. So for this, we have analyzed the vertical wavelength of the wave structure, which is obtained using the plane wave solution, and later on we use this vertical wavelength to estimate the horizontal wavelength from the dispersion relation. Now for this particular case, the horizontal wavelength is found to be around 413 kilometers, which is close to the 450 kilometers as seen by the GD observation. Now we move forward to check this this study for all the 48 cases where the periodic EPBs has been seen, and we see that both these wave parameters are showing a very good correspondence between them on case by case basis. However, EPB did not grow overhead on all these cases, and there are several cases where EPB has gone far west of Gadanki. Now this correspondence, good correspondence means this wave structure are extended over large longitude zone and providing suitable seed structure for the EPB to grow. But however, this mere presence of this wave structure doesn't guarantee the overhead growth of EPB on a particular night. Now we move forward to see if there are any relation with the RT growth rate with the occurrence or non-occurrence of EPB. So for this analysis, we have used only the local RT growth instability, Because we don't have any field and integrated measurement, so we opted this equation. This equation opted from equation number 25 of 1996, where the first term shows the electric field term is obtained using the vertical tip of the ionosphere, and this is the bottom side density getting is obtained using the EPS for the observation, and this mu ion has been calculated using the following formulation given in Kelly 1989, where the height has been considered the bottom height of the ionosphere as obtained using the DPS for the observation. Now the height dependent values are obtained using MSI as 19 model. Now this is the this figure shows the day-to-day variability of this growth rate gamma for the year for the month January to April for the year 2015 and 16. Now these EPB and non-EPB cases are marked here with different color. We can see when the gamma is greater than 11 × 10⁻⁴, these cases associated always associated with the EPB cases, and when gamma is less than 10 × 10⁻⁴, these cases are associated with both an EPB and non-EPB cases. So based on only the growth rate, we cannot say whether EPB will grow on a particular night or not, overhead or not. So we move forward to see whether this growth rate of RT instability is having any kind of relationship with the onset location of EPB. So for this analysis, we have obtained the location of EPB onset within the scan domain of GIRI directly from the scan map, and whichever has grown outside this domain, we have used the backtracking methodology given in Foucault. Here the top line shows the cases where the EPB has grown within the scan domain, and these are the backtrack EPBs. From this the figure, you can see that whenever EPB has grown within a zonal distance of plus minus 120 km around Gadanki, let's say around 1 degree in longitude, the growth rate of gamma is always higher, with the value greater than 11 × 10⁻⁴. And wherever EPB has grown outside this domain, the values of growth rate is limited to less than 10 × 10⁻⁴ second inverse. Now all the non-EPB cases are also found to be associated with the gamma less than 9 × 10⁻⁴ second. So it means that whenever EPB has grown within the zonal dimension of zonal distance of plus minus 120 km around Gadanki, the atmospheric condition over Gadanki was conductive for the overhead generation of EPB. And whenever EPB has grown outside this domain, the atmospheric condition over Gadanki was not supportive to for the overhead generation of EPB on this particular nights. Now this means that there are local scale processes that are deciding this controlling this overhead generation of EPB on a given night. Now we verify this result from the CNOPS-based observation. Now this particular observation is obtained on 10th February 2015, where the two passes, consecutive passes of the CNOPS has been shown here. When the first pass was made, that time the local time of Gadanki was around 1905 LT, and here the location of Gadanki is also been marked here with the red arrow. In the first pass, when we are seeing at the time the EQSB dip over Gadanki was found to be limited around 50 meters per second, whereas the EQSB dip in the western longitude are found to be much suitable or much higher as compared to what we see over Gadanki. Now in the first pass, we see the density map. We can see one depleted structure can be seen around 98 longitude eastward to Gadanki, and when we do see when we see the perturbation, density perturbation, we can see some small scale perturbation also present. In next pass, when the local time was Gadanki on 2045 LT, that time we can see one EPB structure and has been can be seen at the western longitude of Gadanki. And this past case, whatever we have seen, this EPB structure, it has moved further eastward at the time, and we cannot see in the next pass. When we see the density perturbation, we can see along with this deep depletion structure, there is some small scale perturbation also there, and this small scale perturbation can be seen to be generally separated by 480 to 720 km. Now these two structures, which are seen just west side of Gadanki, can be seen to be separated by 600 km. Now this is the same day observation over Gadanki. On this day from GIRI observation, we can see two EPB plumes has been generated, can be seen over Gadanki on this particular night, and this map shows the Doppler velocity within this plasma bubble, and we can see there is a predominance of westward electric field in this bubble can be seen. Now from the zonal scan map, we can see that these two EPB has generated far west of Gadanki, and it has been seen over Gadanki at a much later time due to the eastward motion. Now, if we can use this back trajectory method and to see whether this EPB has been formed, we can see that the location of these EPB are found to be around 190 km and 1540 km westward of Gadanki. Now we can see from the this scan map also we can estimate their interval separation, which is found to be around 550 kilometers. Now this is the same day observation using the DPS-40 observation over Gardanki. We can see that the bottom height of the ionosphere was found to be limited around 350 kilometers, whereas the electric field over so vertical dip over ionosphere over Gardanki was found to be around 80 meters per second, which is very close to the observation as what we see in Sinop observation. Now, if you can, when you estimate the growth rate of Arctic instability on this particular night, we find that the growth rate of Arctic instability was around 6.8 × 10⁻⁴ second inverse. So the condition, ionosphere condition over Gardanki was not suitable for conductive for the over generation of EPB. As also we can see from the ED observation, as also in a Sinop observation, that EPB did not go over Gardanki on that particular night. It has been generated far west of Gardanki and it has drifted at later nights. Now, when we estimate this, their zonal wavelength from this downward propagation, it is found to be around 525 kilometers, so which is very close to the interval separation, as well as what we see in the interval separation when this is these two structures is 600 kilometers. So these wavelengths are matching nicely.
Dr. Suman, you have 3 minutes.
Again, sir, it's just dark actually. Okay. Now this is the summary and conclusion. We can from this study we can say the LHW has played actually a critical role in defining the longitudinal preference for the growth of Arctic instability as well as the EPB. Now LHWs with horizontal wavelength in the range of 200 to 660 kilometers seems to be acting as a seed for the growth of Arctic instability. Now we can see for the observation that Inoson Day observation has a great capability in understanding the day-to-day variability as well as prediction of EPB over within a zonal distance 120 kilometer, or it is a 1 degree longitude around this observation station. However, they are insufficient to assess the growth of EPB outside this longitude zone. Now, based on the observation, we can conclude that Inoson of the network, which is distributed in the longitude and preferably separated by 250 and 300 kilometers to 300 kilometers, would be an important prerequisite to understand the day-to-day variation in the as well as any kind of prediction or future prediction of EPB that has to be done for a given longitude sector. Now, this particular study has been published in JGI Space Physics. So, with that, I conclude. Thank you. Hello, sir. Hello.
Yeah, this Dr. Suman, it was a nice presentation.
Thank you,
so now this presentation is open for questions. I have a question. The large scale wave structure that you're mentioning. So basically, as the wavelength of this structure changes, you also showed that it has a bearing on the growth rate of the instabilities. Is it correct?
So growth rate actually it decides whether bubble will occur or not. But this large scale wave structure actually seem to be present on every day actually. Not it is not like that when it will grow or not. But these structures seem to be present on most of the days actually, sir. So it has the growth rate. Whenever this growth rate is satisfying, then only this EPB will found to grow on that over that particular longitude, sir. So that is understanding, sir.
Yeah. No, at one point you were showing that if your wavelength is of a particular scale, then your growth rate is less than a particular factor. I think 10 to the power minus 4. Yeah. And if it is more than that, then your growth rate was different. So what I was asking is why this wavelength or the zonal gradient should have a bearing on the growth rate.
No, sir. Actually, this wave structure. What I'm telling, sir, this wave structure present on every day. Actually, you can say, sir. But
Yeah.
but EPB growth is dependent on the background ionospheric condition over that particular location where EPB will grow or not. That will the background ionospheric condition will decide. Otherwise, this structure will be present. However, if there is any background ionospheric condition will satisfy the growth rate, then only this wave structure will come into play, and it will give the desired spacing of the EPV cell. So this will serve as a seed structure for the EPV growth. However, that thing is there that a background ionospheric condition has to satisfy the growth of arctic stability.
Okay. Okay.
Yes.
Dr. Shripati?
Yes. Yeah, very nice presentation. I just wanted to know, you are talking about large scale wave structures at low latitudes and its relation to the growth of the plasma bubble. But
Yes,
what about equatorial locations? You have not examined, right?
No, sir, we don't have any data, sir, regarding that. So we are staying at a low
I
latitude.
think
So
that
we
may
have
be whatever wavelengths that you see at low latitude, whether it is same what you see at
that is the idea, sir. We have to verify actually, sir.
I think
If we can
that
get some data from
be cross-checked and really.
yes, yes, sir. If you can check this
Yeah, this is what.
actually from equatorial station, that will be very good, sir. Actually, for validation also.
Yeah. Yeah.
Yes, sir.
Yeah, maybe we'll talk more, I think.
Okay, sir. Well, thank you.
Okay. Thank you, Dr. Suman.
Okay, sir. Thank you so much.
Yeah. So now we move on to the next presentation. So now I invite Dr. Nirvikar to hold the rest of the session.
Thank you, Dr. Tarun, for very nicely managing the session so far, including our talk of Suman. Yeah. So the next presenter, I invite Sri T. Venkateshwara Rao, TV Rao, from KL University, Vijayawada. Are you available, Dr. Venkateshwara Rao?
Available, sir. Is my screen
please,
sharing, sir?
Please share. You will be talking on automatic detection of sporadic
Detection of sporadic heat. Yes, sir.
Detection of cardioionogram for the study of its effect on F layer.
Yes, sir.
Yeah, we can see. Please go ahead. Yeah. No. Again gone.
Now, sir?
Yeah, now it's okay. Please go ahead.
Is my slide changing?
Yeah.
Okay. Thank you so much, sir. Very good evening to everyone. My name is TV Rao. I am working for the organization Balloon Facility of TIFR Hyderabad, and I am a research scholar at EC Department, KL University, Guntur. So in this session, I'm going to discuss about automatic detection of sporadic layer events from the cardioionogram for the study of its effect on F layer. So the overview of my presentation is introduction, the significance of this work, and the methodology what we have implemented, and the results and discussion. Finally, I will conclude with the conclusions and references. So coming to the introduction part, yes, we all know that ionosphere exists about 80 kilometers to 1,000 kilometers, and it's a very complex system. It is very dynamic in nature. So the geometric storm events from the top side are affecting the structure and complexity of the ionosphere, and the neutral winds are affecting the ionosphere from the bottom side, where it is disturbing the characteristics or dynamic nature of the ionosphere. So to understand or to analyze the ionosphere, we have various equipments or the systems such as GNSS receivers, global navigation satellite receivers, and digital ionosondes such as CADI, Canadian Advanced Digital Ionosonde, and we have very low frequency ionospheric disturbance monitors such as SID. And in this analysis, we have considered the CADI system, which was established in TIFR Balloon Facility during 2011. And the configuration of the CADI system is the output power is 600 watt, and it has a frequency range of 1 to 20 megahertz with the sweep frequency of sweep steps of 1 to 200 and 1 to 400, which is configurable one, and it gives the height resolution of 6 kilometers. The main significance of the CADI system, which is in Hyderabad location, is Hyderabad comes under the northwest region of equatorial ionization anomaly, and these are the examples of the ionograms which the the CADI system is generating. So the first one is the ionogram, which shows the F1 and F2 layer traces, and the second ionogram shows the equatorial spread of sporadic E layer event traces and spread of event traces, and the third ionogram shows the E layer as well as F1 F2 layer traces. So we have considered the ionogram from the CADI, which is in Hyderabad location. So coming to the significance, generally when the safety of the life comes into the picture, such as in case of civil aviation applications, so one should have a continuous user position without losing for a fraction of second. So for that, generally we have to implement mitigation algorithms or the precautionary measures in the navigation communication satellite-based navigation system. So that will be navigation signals are affected by the ionosphere because of the geometric storms which are affecting from the top side, which will be reflected in the ionograms in the form of spread of information, and the neutral winds which are affecting the ionosphere from the bottoms are reflected in the form of sporadic E layer events in the ionograms. So both geometric storm events and neutral winds are affecting the characteristics and the dynamic nature of the ionosphere. So that is directly affecting the signals which are passing through the ionosphere, such as satellite-based navigation system signals and high frequency communication signals. So one has to study the ionosphere to mitigate or to take the necessary precautions for the navigation applications and high frequency applications. And as I said, CADI is generating the ionograms as per the configuration at the Hyderabad location. CADI is generating 144 ionograms per day, and it will be 52,000 odd ionograms per annum. So for measuring the parameters or understanding the ionosphere from one location, we have considered the CADI ionogram from Hyderabad. If you want to measure or understand the ionospheric structure or the behavior of the ionosphere spatially, we have to consider the ionograms from the different locations. So as I said, we have 52,000 ionograms per annum from one location. So we have large number of ionograms from different locations if you include everything. So to analyze or to understand the characteristics, we need to scale or we need to analyze the ionograms in manual mode. So manual mode or auto scale mode. So manual scaling or the analysis will take a lot of time, and it is a tedious job, and there is a probability of entering or probability of occurring human errors while doing the manual scaling or the analysis. So there must be an effective way of scaling or effective way of identifying the sporadic E layer and the spread of events from the ionograms. And we have various softwares like Ideal software, Autoscaler software, we have Eureka software, and the most widely used Artist software also we have. And these are all the commercial factors. And we want to develop a tool which can detect the sporadic E layer and spread of information from the ionograms, which we have developed on a open source platform, and we want to give it that to the users who are working on ionosphere. So that is the main significant, and that is the main reason we have developed the software on open source platform. So the coming to the methodology part, yeah, we have developed the tool with the 4 blocks, the raw ionogram block and filter block, layer segmentation block, and ES detection block. So generally the CADI generates the ionogram in the form of star.md4 file format, where it has the header file as well as the frequency versus height beans inside the MD4 file format. Depending on the integration time, it will generate the number of steps. In case of 10 minutes integration, each file, MD4 file, has 6 ionograms. In case of 15 minutes integration, it has 4 ionograms. So the raw ionogram block, means a display block, will identify and it will read the header content from the MD4 file. And depending on the integration time, it will locate the frequency versus height bins from the particular location, and it will plot with the frequency versus height reference. So once the extraction of the frequency versus height points are extracted from the MD4 file, those parameters belongs to one ionogram. Those parameters are given to the filter, as we have the noise in the ionogram. So we have adopted a sliding window technique for removing the noise from the ionogram. So the filter block will remove the noise from the ionogram, and the filtered noise-free ionogram will be given to the layer segmentation. So we have set the layer-wise parameters. So layer-wise frequency versus height points are separated here. So E layer, the frequency versus height points which belongs to the E layer are separated. F1 layer are separated and F2 layer are separated in the segmentation block. So in this analysis, we are interested in E layer. So we have separated the E layer so that frequency versus height points which are separated in the segmentation block will be given to the ES detection block for analysis. So we have implemented a statistical method for identifying the sporadic E layer events in the segmented block. So once we receive the frequency versus height bins points from the segmentation block, we are arranging the frequency indexed height points in a ascending order, and from every frequency point we are seeing the height points, number of height points. Depending on the number of height points, if the number of height points are more than 5 or 6, which is around 10 kilometers to means 6 into 5, 30 kilometers to 100 kilometers, we are considering it as an ES detection, ES layer. So this is how we are detecting the ES layer from the raw ionograms. Coming to the data, yes, as I said, we have considered the data from the CADI system, which is located at Hyderabad. And we have considered the data during the 2015 year, as it has diurnal change. Means we want to see the diurnal changes and seasonal changes. And the most important thing is it has two geometric storms. Means two geometric storm events are occurred during the 2015 year. One is on 17th March and 23rd June. So that is the reason we have selected the data for 2015. And coming to the results part, as I said, we want to explore the results of the sporadic E layer events and spread of events. So we have gone through some research work saying that there is a probability of occurring the scintillations in the GPS when there is a spread of events in the ionogram. So we have made the analysis during 17th March as well as the 23rd June. And we want to show that there is a impact of sporadic E layer event on F layer. So for that, we have considered the data during 23rd June, 22nd June to 24th June. So we have from here, from this plot, we can see that there is a severe geometric storm on 23rd June. So the indication of the storm means the DST going towards peak negative indicates the enhancement of the storm, and the from the negative point, peak negative point, recovering towards the positive will indicate the recovery phase during this geometric storm event. So we have analyzed the data of CADI system at Hyderabad. So we have seen the sporadic E layer events in the ionogram, but we have not seen any spread of information. So we want to say that we want to address that in case of any sporadic layer events, so that is suppressing the spread of information, and subsequently it is suppressing the scintillations in the GPS. That part we want to elaborate and extend that. So for that, for the June storm, we have examined the data, and we want to extend this to support the effect of sporadic E layer event present, which is suppressing the spread of information, means which is affecting the F layer. So this is the results and discussion we have done during this in this analysis. So coming to the conclusion, yes, we have developed this tool on open source platform for detecting the sporadic E layer events and the spread of information from the ionograms. And the complete module is implemented with the noise, raw ionogram block, noise filter and segmentation and detection modules. And individual block is performance of individual block is evaluated with various classes of ionograms. And we have examined the effect of ES on F layer in suppression of the spread F during the 23rd June geometric storm. And yes, we need to explore further, means we need to analyze further to support this statement. And we need to improve the tool to identify different types of sporadic E layers, because we are very close to the equator. So we have seen only one type of the sporadic E layer. As the means we need to further improve the tool to identify different classes of sporadic E layer events. And these are the references which we have considered during the development of the tool. for identifying the sporadic E layer events from the anograms. Thank you, sir.
Thank you, Dr. T.V. Rao. Now we can take some questions. I cannot see anything. Nobody is raising hand at the moment. Okay, if there are no questions, then I have one clarification.
Sir, yeah.
When you say that the sporadic E over Hyderabad is trying to suppress the African occurrence of the plasma bubble over deep equator.
Yes, sir.
What is that like argument behind this? How do you see this argument?
See, we have gone through some research papers, sir.
Yeah.
Sir, the research work says that the presence of the sporadic E layer is elevating the F layer, which is trying to elevate the F layer in such a way that the spread of information or the spread of is getting suppressed.
Okay, I mean, you try to see that the E
want to elaborate
E layer over Hyderabad at what altitude over deep equator has a mapping effect, and what is the best latitude which will have a direct relation of the occurrence of sporadic E and the suppression, because it has to do with your short circuiting of your electric field in the F region, and then that happens in the E region through the field line connection. So please see that.
Sure,
And,
sir. We need to do further analysis, sir, to support
yeah,
that
and then
statement.
maybe latitude also, you try to see at what latitude you should have Inosonde to have a much better conclusion in this regard.
Sure, sir. Thank you.
Thank you.
Yeah, thank you so much.
Thank you. I do not see any questions. Then I move forward for the next talk. Pawan, are you there? Pawan Chaitanya from National Atmospheric Research Laboratory.
Yes, sir. I'm there, sir.
Okay. So then please, I can see your this thing. Please share your screen. Yes. Now we have next speaker, Pawan Chaitanya, ionospheric vertical plasma drift model developed for the Indian and Indonesian sector. Yeah, please share your screen. I can see your screen, but it's not moving and this is not in full screen mode.
Sir, now, sir, it's okay, sir.
No, nothing is moving as such.
Now it is in full screen mode, sir.
No, I think you have to, when you are sharing, that first option is coming, that share full screen, that you have to.
No, it's moving, Nirvikar. It's, okay. I think it's, we are seeing it fine here.
Okay, then fine. I mean, I have some issue with my
terminal,
maybe. Yeah, yeah. Please go ahead then.
Okay, sir. Good evening to all. My name is P. Pawan Chaitanya from NARL. I'm going to talk about ionospheric vertical plasma drift model for the Indian and Indonesian sectors and its validation and usefulness. First, I'm going to tell how we have estimated vertical plasma drift. What is the motivation for development of vertical plasma drift model for Indian and Indonesian sectors? And I will show the performance of the model and its comparison. Finally, summary and conclusion. As we know that vertical plasma drift plays an important role in plasma distribution and the generation of plasma irregularities. It is responsible for many equatorial ionospheric processes such as equatorial plasma bubble, equatorial ionization anomaly, and the formation of additional layers. Direct measurement of vertical plasma drift only possible through incoherent scatter radar. There is there is only one incoherent scatter radar in the equatorial location, that is located at Jakarta. Climatology of vertical plasma drift has been established very well for the Peruvian sector using Jakarta incoherent scatter radar. In 2004, Chow and Woodman suggested that Doppler velocities from radar 150 km echoes can be used to estimate the vertical plasma drift. We tried to detect the 150 km echoes using Gadanki MST radar, and from India, and equatorial atmospheric radar from Indonesia. Finally, we succeed in that. This shows the 150 kilometer echo SNR and Doppler velocity from Gadanki, India, and Kota Tabang, Indonesia. Height averaged Doppler velocity. This bottom panel shows the height averaged Doppler velocity represents the vertical plasma drift. We validated these observations using synapse measurements. We found that there is a good agreement between radar measured vertical ecraspeed drift and synapse measured vertical plasma drift. We made comparison of vertical plasma drift from Gadanki and Kota Tabang. We found that drift velocities at two locations compare well on some days and differ remarkably on some other days, despite the fact that these two radars are longitudinally separated by 20 degrees only. And also, day-to-day variation in drift velocity at two locations are very different. To predict the ionospheric phenomena at one place, one cannot use vertical plasma drift from one place to another place. We have plotted the Searles-Fair model values for Gadanki, Kota Tabang, and Jikamarca. We found that Searles-Fair model does not giving the seasonal variation Indonesian sectors. This model nicely giving the seasonal variation over Peruvian sector because 90% of the input data from Jikamarca ISR radar, incoherent scatter radar. This model may not be suitable for Indian and Indonesian sectors. Finally, we have developed a neural network based vertical plasma drift model for Indian and Indonesian sectors using plasma drift values estimated using radar 150 kilometer echoes. We have used feed forward error back propagation algorithm to train the network. We successfully reproduced the vertical plasma drift values for Indian and Indonesian sector. We compared the model values with observation. We found that there is a good agreement between model values and observation. And also model is giving successfully delivering the day-to-day variation. This shows the model comparison for Indonesian sector. We found that model values are agreed very well with the observations. This shows the seasonal variation of model drifts over Indian and Indonesian sectors. Model drift shows seasonal variation with equinoctial maxima. This feature is well known over Peruvian sector. I have compared two models from Indian and Indonesian sectors. We found that model is individually representing the values for India and Indonesia. There is a large difference between these two models. Finally, the summary is we have developed a neural network based daytime ionospheric vertical plasma drift model for Indian and Indonesian sectors using radar observations of 150 kilometer echoes. This model is first of its kind from Indian and Indonesian sector, presenting local time, season, and day-to-day variation. This model successfully reproduces the daytime vertical plasma drift with maximum error of 2.7 meter per second. The model vertical plasma drift shows seasonal variation with equinoctial maxima, very similar to those of Jikamarca, a feature that is well known. Comparison of model results with observation clearly indicates the potential of the model for studying the equatorial electrodynamics in the Indian and Indonesian sectors. Thank you.
Thank you, Dr. Pawan, for very nice elaborate presentation on your recent effort towards modeling the equatorial ionosphere. Now we can have some questions if somebody want to ask.
Yeah, there was a question from Shashi Singh.
Acha, but yeah, he can.
Yeah, Dr. Shashi, you can ask your question.
Like, looks like he's not online, I think.
Can I ask a question?
Yeah, please, sir, go ahead.
Yeah.
Yes, sir. Yes, sir.
If I understood correctly, what you are mentioning is that the vertical drifts as observed over the Indonesian longitudes and Indian longitudes, they are different, right?
Yes, sir. Correct, sir.
And they are different because of the latitudinal differences or the longitudinal differences?
Sir, it's a longitudinal difference, sir.
Longitudinal differences.
Yes, sir.
But then our understanding is that the electric field, if I understood correctly, 150 kilometer observation is a direct indicator of the prevailing electric field, right? Large scale
Yes, sir.
electric field.
Yes, sir.
And so if it is so, then it should be corresponding because it's a large scale electric field. So it should be representing the ionospheric movement well over Indonesian longitudes also.
Yes, yes, sir.
Is it correct to assume like that?
Yes, sir. It's correct only.
Then why do we see a difference?
I think, sir, there is a wave force structure in the electric field.
Okay. So
that,
okay.
Yes,
but
sir,
that is fixed in time, right? That's
yes, yes, sir.
that structure is fixed in time.
Also, local dynamics may play.
Yeah.
Yes, sir.
All right. All right. Okay. Thank you. Yeah.
Thank you, sir. Thank you.
Yeah. If there are no further questions, I have one small clarification, Pawan.
Sir, sir.
Have you compared your model, the model which you developed using this neural network, with the climatic model of Belafare?
Yes, sir. I have compared, sir.
Okay. No, not over Indonesian sector.
Yes, sir. I have compared.
That model will give no issues. I mean, mostly longitudinally, that model may be symmetric.
Yes, sir.
Just you see, check it.
Yes, sir. Yes, sir.
Okay, fine.
Thank you, sir. Thank you.
Okay. Okay, then. Thank you. Thank you, Pawan. Thank you.
Thank you, sir.
Now we come to the last talk of today's our session B. Miss Ankita Hazarika. Yes, from Dibrugarh University. Are you live now?
Yes, sir.
Okay. So you are able to listen to me?
Yes, sir.
Okay. So please share your presentation now. Performance evaluation of IRI plus and SAMI2 models during solar minimum around 100 degrees east longitude.
Is it visible, sir?
Maybe Tarun sir, please advise. I have some delay at my PC.
Yeah, we are not seeing the presentation as yet. Yeah, if you can share your entire screen, Ankita.
I have already shared, sir.
Okay, we'll just wait because there could be a delay.
Full screen mode, it is not there now.
Okay.
I can see. You have to share.
It is already in full screen mode.
You have to share when you are sharing. It should be complete screen. Yeah.
Yes, it's there now.
Yeah, please go ahead.
Yeah, please go ahead.
Okay. Good evening, everyone. I'm Ankita Hazarika from Dibrugarh University. The topic of my presentation is performance evaluation of IRI plus and SAMI2 models during solar minimum around 100 degrees east. These are my table of contents. Now let's start with the introduction. A critical question in ionospheric physics is the state of the ionosphere and relevant processes under extreme solar activities. The solar activity during the minimum of solar cycle 23 and 24 was record low and unusually prolonged, and thus it gives us an opportunity to explore this issue. During this extremely low solar activity period, the changes in the upper atmosphere and ionosphere were very interesting. The UV irradiance was approximately 15% lower than that of the previous solar minimum. The thermosphere contracted to record low during this period, and also the effect of tides and wave originating at lower atmosphere were stronger at thermosphere and ionosphere, due to which a complex change in plasma drift and wind were also present during this solar minimum period. Thus, this solar minimum period gives us an opportunity to understand the state of the ionosphere and other physical processes during extremely low solar minimum conditions. Now, moving on to the motivation. The significance of understanding the solar minimum lies in revealing the nature of solar variability, estimating the predictability of current models, and also understanding the drivers of global climate change and upper atmosphere changes. Thus, this extreme solar minimum between solar cycle 23 and 24 is a unique case to test the limits of empirical and physical models. And also our study location is 100 degrees longitude sector, which is dynamically different from other longitude sectors, because this longitude sector is within the strongest case of longitudinal WN4 structure, and hence the equatorial vertical drift is a TC except the so enhanced characteristics. With this motivation, the IRI plus and SEMI2 models are simulated during extended solar minimum period 2009-2010, and also during the recent solar minimum 2018 and 2019. The simulated data is then compared with the quiet time TC observations from a chain of GPS station along this longitude sector. Now moving on to the approach, the parameter used for our study is total electron content, which is taken from GPS receivers located at Dibrugarh and Aizawl, and also from IGS stations Havelock, Cocos Island, Kunming, and Port Blair. The models used for our study are IRI Plus and SEMI2 model. Now IRI Plus 2017, which is the IRI extended to plasma sphere model. The IRI Plus is the upgraded version of IRI model. The plasmaspheric density profile in IRI Plus is taken from Russian standard ionosphere plasmasphere model. With IRI, it is possible to calculate VTC to the height of the satellite. In this investigation, we use space weather survey of the to the plasmaspheric extension. The IRI Plus algorithm allows the upgradation by adjusting the model algorithm with the external data, and thus providing the instantaneous values of ionospheric key parameters FOF2, TEC, and SMF2. To calculate the instantaneous value of FOF2 after assimilating with TEC, this formula is used, where the FOF2 is the instantaneous reconstructed value of critical frequency. FQF2 is the CCIR predicted quiet time reference critical frequency. TEC input is the external TEC, and TECQ is the pre-feed TEC, which is calculated by numerical integration of electron density profile generated by IRI CCIR. Now moving on to the SEMI2 model, which is a low latitude theoretical model. It treats the dynamical and chemical evolution of 7 major ion species and electrons at altitudes starting at 90 km to 20,000 km. The empirical models used in SEMI2 are given here. In SEMI2, the neutral density and temperature is taken from MCS model. Neutral wind is taken from SWM93 model. Charles-Fraser vertical drift model is used for vertical drift, and UVAC model is used for ionizing UV. In SEMI2 model, it is possible to customize these empirical models according to the geophysical conditions observed. Now moving on to the results and discussion. First, we see the comparison with IRI Plus model. We use the IRI Plus model in 3 different modes. We use the no input option as a reference point, and then we use GPS TEC assimilation mode and GIM TEC assimilation mode. This graph shows the comparison of seasonal diurnal variation of observed TEC with TEC simulated by IRI plus model with 3 different modes over the 4 different stations for both hemispheres for 2009 and 2010, and this is for 2018 and 2019. These are the seasonally average at 10.7. For a better representation, we also plot the variation of DTEC, that is the difference between the observed and modeled TEC for the same space-time configuration. From these figures, we can see that with no input option, IRI plus overestimate the observed TEC for all stations and seasons for both solar activity period. However, with assimilation of GPS TEC and ZIM TEC, the model simulates the observed TEC quite well for all stations and seasons during both low solar activity period. Thus, we can conclude with no input option, IRI plus highly overestimates the observed TEC during both solar activity period. This may be attributed to the lack of representative database included in the model from a comparable solar minimum. And also, the plasmaspheric model used in IRI plus may need further modification for extremely low solar activities. GPS TEC simulation significantly improved the model performance, and ZIM TEC simulation significantly improved the model performance. Thus, we can see with assimilation of TEC, the model shows better performance. This may be due to the improvement in rescaling the topside profile of IRI plus model due to the external TEC assimilation. Now moving on to the comparison with SEMI2 model. We use the SEMI2 model in 3 modes with no modification mode, and then we modify the neutral density and temperature model using the scalars from Imart and Sifrin, which is found in the literature. And then we modify the UVSE model. Here we reduce the UV model by 15%. This shows the comparison of seasonal variation of observed TEC, which is simulated by SEMI2 for 2009 and 2010. This is for 2018 and 2019. This gives the difference of observed and model data for the same space-time configurations. From the figure, we can see that SEMI2 overestimates the observed TEC most of the time. With modified UV, the SEMI2 simulates the observed TEC quite well. However, the modification and density and temperature could not improve the model performance. Thus, the overestimation observed by SEMI2 may be also attributed to the lack of representative database included in the empirical models used in SEMI2 from a comparable solar minimum. We see that the modified neutral density and neutral temperature could not improve the model performance. This may be due to the there may be additional modification needed in the neutral density and temperature due to strong tidal effects during the low solar activity, and the neutral wind may play also additional role in observed TEC. However, the modified UV model exhibits better agreement with observed daytime TEC. It was also reported that during the extremely low solar activity period, the E-cross-B drift shows different characteristics, including an early afternoon downward drift and a weak or non-existent pre-reversal enhancement. The drift model used in SEMI2 is Charles-Fazer model, and it was reported that Charles-Fazer model failed to reproduce the changes observed in E-cross-B drift. This figure shows the seasonal diurnal variation of vertical E-cross-B drift simulated by Charles-Fazer model for 2009 and 2010 for 90 to 100 degrees longitude sector. From this figure, we can see that the drift do not move downward till 20 LT during equinoxes, and during solstices, the drift do not move downward till 18 LT. Thus, The absence of large upward drift during daytime and pre-reversal enhancement may also play an important role in observed TEC. Thus, we can conclude IR plus highly overestimate the TEC during both solar activity period, and this may be attributed to the lack of representative database included in the model from a comparable solar minimum. The plasmaspheric model included in the IR plus may need further modification. The SEMI2 also overestimates the TEC most of the time. With a modified UV, the model however, there may be additional modification needed to the neutral density and temperature due to strong tidal effects. The neutral winds can play an additional role in modulating the resultant ionosphere density and composition. The drift model used in SEMI2 should also replace or modified for low solar activity period. That's all. Thank you.
Thank you, Ankita, for very nice comparison between IRI and SEMI2 and its comparison with observation. I will take any questions are there on your talk. I do not see any hand raising right now.
Can I ask a question?
Yes,
Yeah. First of all, Ankita, a very nice presentation. I liked your slides very much. Very modern slides.
Thank you, sir.
So my question to you is that at one stage you were mentioning that your EUVAC model, you needed to reduce the flux by 14%. Did I understand correctly? That is like you needed to reduce the flux in order to match the TEC with the model?
We observed it overestimate the observed TEC, and it was reported in literature actually that the UV is reduced by 15% during this solar minimum period. And however, it was also mentioned that this EUV SE model could not simulate this EUV which was observed during this solar minimum period. That's why we reduced the EUV by 15%. This was mentioned in the observed results.
Okay, but then did it affect your other distribution, like the if you consider the electron density distribution, whether did that affect? I mean, you may get a TEC variability correctly, but then did it affect your ionospheric density, say for instance, distribution of the density?
Yeah, maybe it could affect it, but we are not doing that part actually. We are not saying this may affect the density profile. But
yeah, I understand that. Okay, so maybe you should look at it in totality with the distribution of the ionosphere, and then see the TEC whether that is more comprehensively reproduced.
Yes, sir.
Yeah. Okay. Thank you.
Yeah. I think if there are no questions, I have one or two clarifications. Just if I'm not adding to the time because already this is last presentation. So yeah, just one small query that your IRI, how did you assimilate? I could understand your SEMI2 assimilation because there are Fortran programs there. We can go and change little bit input and all. But in IRI, it's like how do you assimilate the data, the GPS data?
So we are using the online version of IR Plus model. It is an online model.
Sorry?
Which is available at INOLab. This IR Plus model is an online version. I'm using the online version. Yes.
Oh, have you mentioned that in methodology somewhere? I missed it.
Yes.
Okay.
Here I have a option.
So if it is through INOLab, then what INOLab is doing, are you aware of it?
Not exactly, sir.
Exactly. Maybe you look into it in more detail that what INOLab people have done for data assimilation.
Sure.
Because again, like it depends on like you have done for seasonal variations, and for whole year you have run. So whether the INOLAB is really that kind of efficiency is there in that. What I see now, why my comment is coming is because when I see your GPS TEC profile, which is observed with your standard deviation markers, they are mostly matching with your model. So looks like that the very high weightage is given to TEC within the assimilation. So actually you are reproducing the TEC from the data itself, not the model performance. That's what I feel. So how do you verify? Assume that you have assimilation today and you are predicting tomorrow, because it's a model, na? So once you have a model, then can you do that? All this like you do data assimilation in the model, either Summit or IRI using IONOLAB, and then you use this model for getting a TEC which is not there in your observation. Like other than the observation period, can you do that? And then compare with the independent observation. Because your observations are going into model, and with the same observation you are comparing, then how it will work out? I'm not getting.
Sir, I'll look into it.
Yeah, I can see that INOLAB. So this is a simple equation of the F-layer parameterization with input and output. I don't think it will, like you need to go into it, what they are doing with the TEC data. And without TEC data, can you really do that model forecast? Once you have INOLAB TEC ready, the model ready, then can you give me, like next month, you have assume August 2009. Can you give me September 2009 from your model output?
Sir, I'm not getting.
Okay. Anyway, I think I will discuss with you later. Just see that when you say it is a model, a data assimilative model, then the model should be independently verified without the data which you are putting into it, so that the performance of whether the model is working or the data itself is coming out as part of the process, mathematical process, that needs to be separated out. That's the only comment. Thank you.
Okay, sir. I will do it.
Yeah,
Thank
please
you.
do. Yeah. Sir, Tarun sir, please. Now it's the end of the session.
Yeah, Dr. Nirvikar, thank you very much. So it was a nice, very interactive session today.
Yes.
So we have come to the end of first day's proceedings. So now I think we'll hand it over to Dr. Kishore, and then we'll meet tomorrow.
Okay. Okay, sir.
Good evening to all. First of all, I want to thank Dr. Tarun and Dr. Nirvikar for conducting the session very lively and giving opportunity for asking all the questions. And I also thank all the participants and speakers. They were keeping the time except one or two, and very nicely made presentations, and they prepared very well. And all the latest happening in the ionosphere today we could see. I thank all the speakers, and meet tomorrow at 2 o'clock. Okay, good night.
Yeah, thank you, sir. Thank you very much.
Thank you to all the conveners, co-conveners, chairs, and co-chairs for this session. And with this, we come to the close of the first day of the second plenary session of the symposium. Thank you all.